comes in. So harmonics and electric power. It's a brief background on harmonics. I'm sure you're all familiar, but if we take a square wave is the Taylor series of an infinite sum of sine waves at different frequencies. So we have a fundamental. We potentially have a third harmonic that's 3 times the frequency and a third the amplitude. A fifth harmonic, 5 times the frequency, a fifth the amplitude, 7 times a seventh the amplitude. And what we're going to find is that we find a lot of harmonics in our AC signals. And if you have an inverter, it's even more harmonics. So these are going to be really relevant things when we start looking at values like RMS. So what happens if we do that? So again, I was just working in kind of the simulation mode of our software. I took our voltage and our current from the previous section, and I added some harmonics. So I took a 60 hertz, 30-degree phase shifted current, and I added a fifth harmonic and a seventh harmonic. And you can see 5 times 60, 7 times 60. Next, for the voltage, I again took my sine wave, not phase shifted, and then I added a lot of fifth harmonic and a lot of seventh harmonic. And we can see in our example here, in the blue, I have my voltage that's got those really kind of drastic peaks in the sine wave. I've got my current that's got some shape, but not nearly as much as the voltage. And I'm going to do some calculations on these, and we're going to see what happens. So we'll start off with our instantaneous power. We'll start at the same place we did previously. So what we see is I've got my power in my aqua, and we can see that, I'm just taking P is I times V. And we get this really jagged waveform because that multiplied product is following the shape of those voltages and currents. And in the black, I have my average, and down here I have my zero. And we can see that we get a lot of oscillation in that power. And if we remember the definition of reactive power, it's that oscillation in power. So we see that oscillation, and we have, again, that negative power. Here's our reactive element, that positive negative counterpart. So to really start understanding this and really start describing these things, we can see how difficult that would be. So we want to use our RMS and our average powers. And again, I can't stress enough that these oscillations in powers indicate that there's a lot of reactive power, and we're going to find that in a moment. I give away all my secrets ahead of time. So we take that waveform that we had previously, our voltage, our current, our high harmonic power, and we'll kind of break it down by what we're doing here. So we have this full bandwidth data. It was 500 kilosamples per second was my simulation rate with a 50 kilohertz filter. So this is all the glory. I don't have anything happening nearly at 50 kilohertz, but then I calculate my RMS voltage, current, power, reactive power, parent power, and I find these graphs to be pretty boring because they're constants. But you can see we have this voltage, current, apparent power, real power, reactive power. And if I run my calculations and I measure my values, we can see my IRMS 72 amps, VRMS 412. Keep this number in your head. Our apparent power 30 kVA, real power 24, reactive power 16 kVAR, and then our fundamental phase is 0.52 radians. Fundamental phase is that phase shift between, we'll use the zeros here because those are a lot more obvious. Our voltage zero and our current zero. It's the phase shift between those two. Remember, this is 30 degrees. And we have a power factor, and we're going to define power factor as P over S. So real power over apparent power of 0.827. Now, if you remember back, we had a couple equations for reactive power, and I think we should look at those. So we had reactive power is the root of S squared plus P squared. Straightforward enough. Oh, minus. So we have 30 squared minus 24.9 squared. We get 16.9 kVAR. That's that same number I have here. Cool. That works. That makes you put up that other equation. We have voltage times current, so VRMS times IRMS, times the sine of theta. Well, I've got a theta here. What if I plug this value in right there? And we multiply that out, and we get 15.1 kVAR. Why are these two values different? This is where the questions start coming. Well, this is the fundamental phase. So this is the phase just of those zero crossings. This doesn't actually take into account all of the reactive power there is, because we need to consider that V and I have harmonics. And each one of these harmonics has their own amplitude and phase. So if you wanted to run this equation, you would need to do a lot more math. So phase in theta is for the fundamental only. Each harmonic should have their own phase angle if you really want to dig into the details. Power also contains harmonics. That power, that real power we're getting, we can measure this. This does have harmonic content to it. That harmonic content is going to change that power value. Higher or lower, it's altering it. So we really do need to consider power factor as P over S instead of the cosine of theta that we're all probably familiar with. So keep that in mind, and we're going to see this theme over and over. Okay, we've addressed that difference. These are full bandwidth RMSs, that 50 kilohertz filter rate, and we're using a phase angle that's for the fundamental. That's going to be a common theme. So let's take the next extreme example. Let's look at just the fundamental. So these are those same exact signals, except now we're only looking at the fundamental. We've effectively filtered out all that harmonic content. And what we see is, if we look at the waveform itself, we can much more distinctly see that phase shift. We can see our power has that nice sine wave, but it's not jagged anymore, and we still have a little bit of reactive power, and our average power is kind of right in the middle. So this is a little more elegant, but it doesn't have as much information. And again, I run my equations, and we see these very boring kind of flat lines. Well, one thing worth noting is that now my real power and my reactive power are almost the exact same, and my apparent power is way down here. And if we run those exact same equations we ran last time, the exact same equations, just on data that's now had the fundamental isolated, we can see our IRMS decreases, our VRMS decreases from, I believe it was 412. So we have that big decrease here, almost 60 volts. Because our RMS has changed, our S, I times V, is now 25 instead of 30. Our power is the same, because power is that real power. We can physically measure that and average it and trust that. Our reactive power is now significantly lower. And if we look at that phase angle, that's still 30 degrees or 0.527 rads. That's because filtering doesn't change our signal in time. And now we look at our power factor and we get P over S of 0.993. So I think this is really important because this is highlighting that with the same data, we can get two very different interpretations. So standard RMS includes fundamental and harmonics. Oh, got too far ahead of myself. Each harmonic has its own RMS and phase. And what we find is that equation, V times I sine of theta, is dependent on V and I being calculated for the fundamental. It's also dependent on power being the fundamental power. So we have an equation in our software called fundamental RMS, where we actually remove all the harmonic content and just look at the content of the fundamental. It's similar to a THD calculation. And we find that using that exact same equation, what previously was 16 kVAR is now 2.7 kVAR. And if we line up kind of those stats side by side, the full bandwidth and the fundamental, power is the same. IRMS is slightly smaller. Now, if we remember that VRMS had a ton of harmonic content in it comparatively, 412 to 353. That big change is influencing S, and it's influencing Q. And we see this huge difference between reactive power. And again, the exact same data. but the interpretation of it's drastically different depending on how you look at your signals. Cool. We've kind of set up this theoretical example, and I showed a really nice point. But what happens if we step into the